Today I will be dealing with Euclidean geometry in mathematics. So Euclidean geometry, we all know that it is a circular geometry. It all deals about circles and quadrilaterals. So now I'm going to do a little bit of revision. So this revision is going to cover grade 11 theorems. So in grade 11 we did 9 theorems, if I'm not mistaken. So those 9 theorems were covering circles and quadrilaterals. So now I'm going to start with theorem number 1. So these theorems are not in order. I'm not doing them according to the order. I'm just going to discuss them randomly. So the first theorem is theorem 1. So theorem 1, we all know that, like, when you look at our circle, in our circle we have what we call a chord. This line is a chord, we all know it. It's a chord. And then this is just a line. And then here we have the center. This is the center of our circle. So theorem 1, it says that the line drawn from the center of a circle to midpoint the chord, it bisects the chord. It means that if a line is drawn from the center of a circle and then that line meets the chord, it divides that line into 2 equal parts. That's why they use the word bisect. So it bisects that line, it divides that line into 2 equal parts. So it means that this line is going to divide our chord into 2 equal sides. So this side from here to here is going to be the same as from here to here. So let's just give our circle variables. So let's say here we have A, and then here is B, and then C, and then E. So it means that if this is our center and then this is our chord, therefore BC is going to be the same as CE in length because of this line bisects our chord. So the reason we say that BC is equal to CE, BC is equal to CE, our reason why is the line drawn from the center of the circle to midpoint the chord, it bisects that chord. So that is the first reason. So it's important for you to know this theorem so that you can be able to apply it in questions. And then another theorem, it says the angle at the center is 2 times the angle at the circumference. So this is our circumference, this whole circle, we have the center of the circumference. So the angle located at the center of a circle, it is 2 times the angle at the circumference. It means this angle is twice the angle that is at the circumference. So for example, let's say we have 2 here. So if we have 2 here, then we have to find this angle. We know that according to this theorem, the angle at center is twice the angle at the circumference. So it means this angle is going to be 4, because we have to multiply this 2 by 2 so we can get the angle at the center. So the angle at the center is twice the angle at circumference. So if we want to find this angle, we have to divide this by 2, and then we get 2. Because of a multiplication and division, we call them the reciprocals or the opposite. If you want to go to division, you multiply. If you want to go back to multiplication, you divide. So it means angle C is 2 times the angle A. Angle C, let's say is C1. So angle C1 is 2 times angle A. this angle is 2 times this angle. Why? The angle at center of a circle is 2 times the angle at the circumference. That is the reason. And then another theorem is this one. So when we look at this theorem, we notice that we have a quadrilateral. A quadrilateral is any shape that is made up of 4 sides. So this thing has 1, 2, 3, 4. So it is a quadrilateral. So we have a quadrilateral, and then this quadrilateral is put on top of a circle. So when a quadrilateral is on top of a circle, we call it a cyclic quadrilateral because of it is on top of a circle. So the circle plus quadrilateral, they form a cyclic quadrilateral. So here it means we have a cyclic quadrilateral. So in short, we call it a cyclic quad. So we have to know like this cyclic quad, it functions in which ways. So let's say we have A, B, C, D, and E. So according to the rules or the laws of a cyclic quad, it says that the external angle, which is this angle, the angle outside, the external angle of a cyclic quad is equals to the interior opposite angle. So it means the angle that is outside of a cyclic quadrilateral, it is equal to this angle that is inside, but opposite to that outside angle. So it means this angle, it is opposite with this angle. So that means this angle, the outside angle, is the same as this internal angle inside. Right? So, and then another, okay, let me write it down first. Angle, let's say it's angle D1, and then here is angle D2. So it means angle D1 is equals to angle B, which is this angle, angle B. Why we say that? I said the external angle of cyclic quad is equals to the interior opposite angle. So that is rule number 1. And then another reason, another rule, it says that the opposite angles of a cyclic quad are supplementary. So it means the interior angles that are opposite to each other inside a cyclic quadrilateral, they must add up to 180 degrees. So the word supplementary means they must be 180 degrees. So it means angle A plus angle C, because of they are opposite to each other, and then they are inside the cyclic quad. So it means angle A plus angle C, always they must give us 180 degrees because of they are supplementary, they are internal, and then again they are opposite to each other. So angle A plus angle C must add up to 180, they are supplementary. So angle A plus angle C always must be 180 degrees in a cyclic quad. Reason being, opposite angles of cyclic quad are supplementary, or they add up to 180 degrees. Another one is that we have angle D2, this internal angle D2 and then angle B. So angle D2 and angle B, they are opposite to each other, and then they are inside the cyclic quad. It means that they are also supplementary. This angle plus this angle, always they must give us 180 degrees. So angle B plus angle D2 always must be 180 degrees. Why? The same reason. Opposite angles of cyclic quadrilateral are supplementary. And then we move to another theorem. So we have this theorem that talks about angles on the same segment. So we have these two angles, they are on the same segment. They are on the same segment. And then the other two they are also on the same segment. So let's say we have A, B, C, D, E. So according to this theorem, angle A must always be the same as angle B because of they are on the same segment. And then again, angle D is always the same as angle E because of they are on the same segment. You can see that inside the letter M. So inside our letter M, so this thing forms M. So this the same the segment, and then it's also the segment. And then this one, it is on an upside M. Our M is looking upward. It is upside M, upside down M. So they are also on the same segment. So angle A is equals to angle B. Why? Angles on the same segment. And then again I say angle D is equals to angle E. Why? Also angles on the same segment. So just for interest's sake, we also have this angle, let's say it's C1 and C2. C1 is equal to C2. Why? When you go back to grade 9, in grade 9 we did this thing, we did something like this. We did these types of angles. They call them vertically opposite angles. So it means this angle is the same as this angle. So you can see we have x here. Our x is looking this way. So that means C1 is equal to C2. Why? Because of they are vertically opposite angles. So yeah. And then we go to another theorem, theorem number 5. So in theorem number 5, we are looking at the tangent. So we all know that a tangent is a line drawn outside of a circle. And then that line only touches the circle at one point. So it only touches the circle in only one point. So that line we call it a tangent. So here we have the tangents that are drawn outside a circle. And then we have two of them. And then all of them, they come from a common point. This is this point. Let's say this point is point T, and then P, and then Q, and then Z, and maybe F. So we can see that these tangents, they come from a common point, which is T. So this theorem, it says that the tangents that are drawn from a common point, that is externally, they are equal in length. It means their length is equal. That's why we have these signs. So it means from here until to P. So TP is equals to TZ because of their tangents from external point. So PT, which is this line, is always the same as ZT. ZT. Reason, we call them the tangent from external point. That is the reason of this thing. And then another theorem can also arise in this theorem number 5, which says that the tangent is perpendicular to the radius is perpendicular to the tangent. Let's say in this thing we have the center of the circle, and then we have this line that we call it a radius. So we all know that a circle has a radius, right? So a radius is half a diameter of a circle. So when we have a radius touching our tangent, it forms an angle of 90 here. So another theorem, it says that always when a tangent meets with a radius, they form an angle of 90 degrees. Why? Because of the radius is always perpendicular to the tangent. So this other theorem, it says that the radius is perpendicular to the tangent. Okay, so then we move to the next theorem, which is this one, theorem number 6. So theorem number 6 we call it a tan-chord theorem. It says that the angle between a tangent is an external line, like I've said. So it says that the angle between a tangent and a chord, we have a chord, we have a tangent. So an angle between a tangent and a chord, this angle, the angle that is located in between, it is equal to the angle at the alternate segment. It means it is equal to this angle. So always the angle between the tangent and the chord is equal to the angle located at the alternate segment. So this angle is always the same as this angle. Therefore, we call it tan-chord theorem. So if we have A, B, C, and D here, so if we have something like that, we are going to say that, let's call this angle C1. So always we're going to say that angle C1 is equal to angle A. Why? Because of tan-chord theorem. Yes. So now we move to the last theorem, which is theorem number 7. So theorem number 7, it says that when we have a diameter in a circle, we all know that a diameter is the sum of radii of a circle, meaning like a radius plus a radius, they form a diameter. So when you have a diameter in a circle and then we have a triangle, therefore this diameter is going to make this angle to become 90 degrees because of it is the angle located at the semicircle. So it is the angle at the semicircle. So it means that if we have A, B, C, so it means angle A always is 90 degrees. Why? Because of it is the angle at the semicircle. How do you see the angle of the semicircle? You have to identify the diameter in your circle. After that, you will be able to identify this angle by following your triangle. Okay, so now I'm done discussing or revising these theorems. So it is important for you to be able to prove some of these theorems. So obviously your teachers, they've shown you which theorems are important. Now I'm going to do a little example whereby I apply some of these theorems to solve my problems. So in our example, we have this question. It says in a diagram, points A, B, actually in a diagram, points A, B, D, and C lie on a circle. CE is parallel to AB with E on AD produced. Chords CB and AD intersects at F. Angle D2 is 50 degrees and angle C1 is 15 degrees. So our question, it says that in a diagram we have these points A, B, D, and C. We have A, B, D, and C. So these 4 points, they lie on our circle. Yeah, all of you can see that they touch our circle. Yeah. And then this point and this point C, point E, I mean, it is produced outside. So and then this E, it is on AD, it is on line AD. So line AD is this line AD. So this point is produced from this line AD. And then again it says that CE is parallel to AB. So these two lines, this line and then this line, they are parallel to each other. So when you hear the word parallel, you have to be alert. Your mind must be alert. It must remind you of some other theorems that were done in the 9, 10, and 11. So I'm talking about these theorems that talks about parallel lines. You can see we have a parallel line, a parallel line, parallel line, parallel line. And we also have this other one of F. We have to know that F is for corresponding angles, Z is for alternating angles, C is for co-interior angles, and then vertical opposite angles. So these ones, like, you have to know them, like it's a must. So now we have this thing, and then after they say that angle C1 is 50, and then angle D2 is 50. So before we can go to the questions, you'll be able to see that we have the letter Z in our parallel lines. We have the letter Z, and then I've just said that the letter Z is for alternating angles. Is this thing? You can able to see it. This Z is from this side, and then again this Z is formed when we go like this, and then when we go like this. So we have Z facing that side and then Z facing this side. Okay? And then after that, we also have triangles, but then those ones are not important. So let's just go to the questions. So the questions, they say that our first question says, calculate with reasons. You have to calculate and give reasons. So calculate with reasons the size of number A. It says angle A for 3 marks. Number B, it says the size of angle C2 for 2 marks. So it means that we have to find angle A. So angle A is this angle. We have to find how much is this angle. Our angle A, it is unknown. So we want this angle A. So in order for you to be able to identify angle A, there are several theorems that we can apply here. As you can see, we have M, the letter M, for the theorem that talks about angles on the same segment, this theorem. We have this M, our M goes like this. We have M. So it means angle A is the same as angle C2. But then C2, we don't have C2. So we won't be able to get angle A. And then again, we have the letter Z going this way. So it means angle A is the same as angle E because of they are alternating angles. So it means we have to find this angle first. Once we get this angle, we know that this angle is the same as angle A because of they fall under letter Z, this letter. So how are we able to get angle E? So in order for you to be able to get angle E, we're going to look at what we have been given. So as you can see, we have been given 50 and 15 degrees. And then we have triangle, this triangle. And then we know that the external angle of a triangle is equal to the sum of the two interior angles. So it means this is our external angle of a triangle. Let me just try to draw it separately. So this triangle is like this. It's like this. The triangle I'm talking about is C, E, and then we have D2 and D1. And then here we have 50. And then here we have 50. So you want to find this angle, angle E. So the other rule of a triangle, it says that the external angle, the outside angle of a triangle, is equal to the sum of two interior opposite angles. So it means this angle is this angle plus this angle. So 15 plus this angle, always they have to give you 50 degrees. So how are we going to solve that? We're going to say angle C1 plus angle E always is equals to angle D2. So it means the sum of interior angles is equals to the exterior angle. So the exterior angle of a triangle is equals to the two opposite interior angles. So C1 is 15 plus angle E, we don't have it, is unknown, and then D2 is 50. So in order for us to get angle E is going to be the same as 50 minus 15. So it's the same as 35 degrees. I'm not sure about my answer because I'm not a mathematician, so I don't know. So angle E, we've gotten angle E. So this is our number A. So we have got like the size of this angle. So we've got that angle E is 35 degrees. But then the question says find the size of angle A. So I've said that angle E is the same as angle A. Why? Because of they fall on the letter Z. So they are alternating angles. So therefore, or we can say but angle E is equals to angle A. Why? Because of their alternating angles. After you say this, you say, why do you say these are alternating angles? Because of CE is parallel to AB. So therefore, angle A is equals to 35 degrees. So we have answered our question for 3 marks. And then number B. So number B, it says calculate the size of angle C2. So this angle. So already, let me put it, we have 35 here. So it says calculate the size of angle C2. So angle C2, I've just shown you that it falls under this letter M. So this letter M, it falls in this theorem, which says that the angles that are on the same segment are equal. So it means that angle C2 is equals to angle A. Why? Because of their angles on the same segment. So therefore, angle C2. So therefore, angle C2 is equals to 35 degrees. Because we've already gotten angle A, which is 35. So C2 is also 35. So we have 35 here. 35 degrees. So now we're going to question number 2. Question number 2, it says that prove with a reason that CF is a tangent to the circle passing through points C, D, and E. So points C, D, and E. So we are concentrating on this point. So this point. So it says that we must prove that this line CF is a tangent to the circle that is going to pass here. So I don't have a color, so I'm just going to use this one. So it means somehow there's a circle that is passing through these 3 points. There's a circle that's going to pass like this. Like it's not a perfect circle, but then this circle is going to pass through points C, E, and D. And then after that, we're going to have something like this. I'm going to draw that sketch of our circle. So we're going to have something like, we're going to have C, E, we're going to have C, E. Let me just try to create a space. So we're going to have C, E, and then D. So in this point we have a line, and then a line, and then a line, and then we have F here. So in this point we're going to have a circle that is passing through those points, something like this, right? You see, so it says prove that CF is a tangent of this circle. So a tangent, I've told you, it's an external line. So you see, it's a tangent, this one. So you have to prove that this CF is a tangent of this circle. So in order for you to be able to prove that, you have to prove that this angle, so this angle is going to be C1. It's going to be this angle. It's going to be C1. Then, no, not C1. Okay, it's going to be C2, the one that we have just put in. This one is going to be C2. And then our C1 is going to be in this side, you see. So C2 and C1. So it means our C2, we've gotten that C2 is 35 already, please. And then again, we've gotten that angle E is 35. So angle E is 35 also. So you have to prove that angle C2 is the same as angle E. So if these two angles are equal in quantity or in amount, if I may put it, therefore this thing automatically becomes a tangent. Why? Because of our theorem here, the chord theorem. We are proving it. We are proving the chord theorem there. This is our chord theorem. You can see this drawing and this drawing are the same. So we are proving this theorem that C1 is the same as A. The angle between a tangent and a chord is equal to the angle in the alternating segment. That's why I've proven it that C1 is equal to angle A. Why? Because of chord theorem. So it means here we are also proving chord theorem. We have to prove that C2, because of C2 is the angle between a tangent and a chord. If we prove that this angle is equal to this angle, therefore automatically CF becomes the tangent. So already we're proving that we've proven that C2 is 35 and then angle E in our previous questions is also 35. So this is what we're going to write. That's why it's 2 marks. We are going to say angle C2 is equals to angle E. All of them they equal to 35 degrees. So all of them equal to 35 degrees. So therefore, since they are equal, CF is a tangent. Why we say it's a tangent? This is the inverse of tan chord theorem. Why do we call it the inverse of tan chord theorem? It is because of when you prove this theorem, you say that CF is already a tangent. So if CF is already a tangent, therefore this angle is equal to this angle. So in our case, we didn't know that CF is a tangent. We had to prove that CF is a tangent. So how were we able to prove that? Firstly, we identified our angles. So we identified angles, and then after we've noticed that these angles are equal, then we deduced that CF is a tangent. That's why it's an inverse of our theorem kappa. The inverse, sometimes we call it the opposite of our theorem. Therefore, CF is the inverse of tan chord theorem. Then we have proven that CF is a tangent. Yeah. So it is very important for you to practice these theorems so that you can be able to apply them in your diagram, because in the exam, they won't be there for you to be able to select which one appears in your diagram. You have to know them in your mind so that when you see the diagram, you are able to identify that, oh, this thing is theorem 2, theorem 4. So once you know them, you'll be able to kill each and every problem that you encounter. So yeah, thank you. I'll meet you in the next video whereby I do a lot of examples that involves these theorems. Thank you.